Students, in this video we will learn about the specific resistance or the resistivity. Okay, you know that the resistance of any conductor is directly proportional to the length of the conductor. Resistance is denoted by capital R and length is denoted by L. Then R is directly proportional to the L and R is inversely proportional to the area of cross section of the conductor. Okay, so R is inversely proportional to the A. Here, why R is directly proportional to the length and why R is inversely proportional to the area of cross section? If you did not get this, watch my previous video. The heading of that video is the electrical resistance. Then you will get this properly. Okay, this is the first equation and this is second equation. On combining these, R proportional L upon A. Okay, we can replace this sign, proportionality sign, by any constant. So here R will be equal, let the proportionality constant is rho and L upon A. This proportionality constant is called the specific resistance or the resistivity of the conductor. So we can find the formula of this resistivity. So here rho equal Ra upon L will be there. Okay. Now we can find the SI unit of the resistivity. So we know that the SI unit of resistance is ohm. It is denoted by omega. And the SI unit of the area of cross section is meter square. And length meter. M will cancel by this M and here remaining part omega M. So the SI unit of specific resistance or the resistivity will be ohm meter. Okay, we can also find the dimensional formula of the resistivity. So from this equation rho equal Ra upon L. The dimensional formula of resistance is mL square minus power 3 and A minus power 2, and the dimensional formula of area L square. Dimensional formula of length L will cancel by this L and remaining part M L square and here L. So here will be L cube T minus power 3 and A minus power 2. So this is the dimensional formula of resistivity. Okay. Now what is the well definition of the resistivity? So from this equation is rho equal Ra upon L. Okay, in this equation, if A equal 1 and L equal 1, then rho will be equal to R. Okay, so from this equation, we can say that the resistivity is equal to the resistance. So what is the difference between them? We can define here that the resistivity of any conductor is numerically equal to the resistance of that conductor whose faces, whose cross-sectional areas are units and the distance between the cross-sectional area is unit. Look at this. This is the conductor. This is the cross-sectional area. This is also cross-sectional area. This is uniform cross-sectional area. That's why the cross-sectional areas will be same, and the length L. A and A also 1, and the distance between two faces, let this is equal 1. Okay, so in this condition we can define that the resistivity or the specific resistance of any conductor is numerically equal to the resistance of that conductor whose faces are units and the different distance or the separation between two faces is also unit. In that case, the resistance of this conductor will be equal to the resistivity of the conductor. So this is the well definition of the resistivity. Okay, now here the factors affecting the resistivity of the conductor. So what factor affects the resistivity of the conductor? We will learn about this. So you know that rho equal R A upon L. Okay, but R equal, in the previous video we had already studied that R equal M N E square tau L upon A. Okay, so on putting the value of R in this equation, this is the third equation. So rho will be equal, the value of R, M N square N E square tau and M N E square tau L upon A. This is the value of R and multiplied by A upon L. So A cancel, L cancel, rho will be equal M upon N E square tau. Okay, this is the expression for the resistivity or the specific resistance of the conductor. Okay, from this equation, here M is the mass of free electrons. Okay, and E is the charge of the one electron. So this is constant and this is also constant. So this rho will be inversely proportional to the N, and this rho will also be inversely proportional to the tau. Okay, and you know this N is the number of free electrons per unit volume of the conductor. Okay, now here if the number of electron per unit volume of the conductor will increase, then the resistivity of the conductor will decrease. Okay, and if the number of electrons per unit volume of the conductor decreases, then the resistivity of the conductor will increase. Okay, now for different conductors, the number of electrons per unit volume are different for different materials. Okay, so you know that this number of free electrons determines the nature of the conductor. Okay, so because this determines the nature of the conductor, that's why, and you know that this rho depends on the N. So we can say that the resistivity of the conductor or the specific resistance of the conductor depends on the nature of the conductor. Okay, and you know that here in this equation, length is not there, area of cross section is not there. So we can say that if we increase the length of the conductor, initial length of this conductor is this, and the in increasing the length, the final length of this conductor is this. If we increase the length of the conductor, because this formula is independent from the length of the conductor, that's why here the resistivity of the conductor does not affect by the increasing the length of the conductor. Okay, and because here in this equation area of cross section is not there, that's why if we decrease the area of cross section or increase the area of cross section, this resistivity or the specific resistance of the conductor does not affect by the area of cross section. It is only affected by the nature of the conductor, and this is the tau. Tau is the relaxation time of free electrons. Okay, listen here. So we can say that if let this is the conductor and here free electrons are there. Okay, now when temperature is increased of this conductor, temperature increased, so this moving electron will collide with this atom. This moving electron collide with this atom and deflects and goes along this direction. Okay, so and again it will collide with this atom. So the distance traveled by the electron, this is the shortest distance between two collision, and time taken between two successive collision is called the relaxation time. Okay, if temperature is increased, then the electron will get more energy and the velocity of electron or the drift velocity of electron will increase. Then this electron will reach to this atom or this ion early. Okay, means the time will decrease. So the relaxation time decreases when temperature is increased. Okay, so when temperature is increased, tau is decreased. So the tau is decreased means rho will increase. Means when temperature is increased, rho is also increased. So rho is directly proportional to the temperature of the conductor. Okay, so two factors are affecting the resistivity of any conductor. Which factors? Here first, the nature of the conductor and the temperature of the conductor. Okay, okay. So here we will learn again that the resistivity of alloy and the resistivity of conductor. Okay, so why the resistivity of alloy is more than that of the constituent metals? Let we consider about the nichrome. Okay, the constituent elements or constituent metals are nickel and chromium. Okay, from this here the charge in nichrome Ni2 plus and the charge on chromium 3 plus. So the size of nickel, sorry, this is the nickel. Okay, sorry. So the size of nickel is smaller than that of the size of this chromium. So in the lattice, in the alloy, here the distribution of ions will different in the alloy. In the nichrome alloy, the distribution of the size of the ions will different. Okay, and through this alloy, electrons are moving inside the alloy. So you know that the electron will come to the nichrome due to the electrostatic force exerted by the nichrome ion. So it will move along this direction. Here chromium is also there, and the charge of this chromium is more than that of the nickel. Okay, that's why this electron will drifted towards this direction. Okay, with the more electrostatic force. So in this condition, after here to here, it will go here from along this direction. Okay, so between two collision, first collision and this is the second collision and other collision. So the relaxation time will decrease of the free electron. That's why when relaxation time decreases, from this formula, 1 upon tau, here resistivity of the alloy nichrome will increase. When tau is decreased, rho will increase. Okay, and in the case of conductor, the size of the ions of the conductor are same. So between two successive collision, the relaxation time will same. Okay, and uh, does not change the relaxation time between two successive collision. That's why the resistivity or the specific resistance of the pure metal is less than that of the alloy. Okay, alloy. So resistivity of nickel conductor will be less than the resistivity of nichrome. Okay, thank you.